Yeah, very good morning to one and all. Today we are going to discuss about the source of errors which we do generally observe in DSP implementations. Some of the errors are like the errors. Generally, if we discuss about the errors, we do observe some errors in the DSP computation because there are several blocks. While we have discussed about the digital signal processor block diagram, in the initial, what is the first front end block of the DSP processor is A to D converter, and before the in that itself we are coming up with a sampling and hold process. After converting the analog signal into a digital signal, we'll be giving that to a DSP processor. That will be a second block, and then we'll be giving the output of a DSP processor as an input to a D2A converter, which it converts this digital signal back to an analog signal. While an analog signal is converted into a digital signal, there may be some errors is occurred due to that conversion process, and there may be the same errors which can there may be a while we are implementing any operations on the incoming signals in the DSP processor. There also there will be a problem of arising some errors in it. And while we are coming to a the last block, which is called the D2A converter, where in order to convert the digital signal back to an analog signal also requires also may create some errors. That errors generally we do observe in digital signal processing implementation. Generally, the errors which are there in DSP calculations are due to limited word length. If we increase that word length or the size of the word length for a data by using rounding instead of truncation, we can be able to reduce the errors. So some of the errors you can observe in A to D conversion while we are converting analog to digital signal. Some of the errors can be observed in D2A conversion also in D2A digital to analog block, and some of the errors can be computationally while you are doing some computational processing in the DSP block. There may be a chance of occurring some errors. So these errors are of different kinds, like quantization error, rounding off error. All these are some of the errors which you do observe. Generally, you will observe quantization error in the A to D conversion, because whenever you are sampling the original analog signal, and while we are converting that to a digital signal, we need to make the sample value to be rounded off to a standard fixed number. That the original value minus that fixed number of value, we are going to rounding of the value is being observed in the quantization. We are truncating there, and generally that difference will give you some quantization error. For example, if you observe that x as a original signal, for example, and x suffix q as a quantized signal, the error can be written as x suffix q minus x. That is what called as quantization error. This you will be observing in A to D conversion errors. And you can also observe a rounding of error, as I said, and that completely depends on the step size. The step size is represented with respect to delta. And there were so many representations mathematically, and few of the block diagrams are also given very well in the avatars in textbook. You can just go through that. And in the same way, you will be observing some DSP computational errors and the digital to analog conversion errors. And that generally in DSP computational errors, you will be discussing about signal to noise ratio. So that signal to noise ratio should be, it will be very high when the number of bits are more, nothing but the word length. If we increase the word length, SNR increases. If you increase the word length, some of the errors may be reduced. All these things depends on the word length, nothing but the number of bits used to represent the signal. That is taken care in order to in order not to have any impact on this impact of these errors on the computation. We should not disturb our original functioning of DSP processor. You need to look after this. And there is another topic called compensating filter. This is a filter which is designed with a frequency response of inverse h of f and place it at the output of D2A converter. and place it. This will be used. This filter generally will be using at the output of D2A converter to compensate the amplitude degradations of D2A converter. Generally, you will be getting a D2A output is itself an step size step staircase signal, that is nothing but different amplitude levels. To compensate that amplitude degradations, we will be using this compensating filter at the output of D2A converter. Generally, such amplitude degradations are due to zero order hole. Such a filter can be of a IAR filter. That compensator filter can be an IAR filter. We have already discussed it about it is infinite impulse response filter. This is what regarding the compensating filter. So the final summarization of the sources of errors in DSP implementations is generally in a DSP system we consist of A to D converter, DSP device and D2A converter. The accuracy of DSP implementation completely depends on the number of factors contributed by A to D and D2A conversions, and how to and the performance of DSP device also. The error in the A to D and D2A in the representation of analog signals is by a limited number of bits is called a quantization error, and the quantization error decreases as the number of bits increases. As I told you, just I'm summarizing it. And the errors in the DSP calculations are due to limited word length use, and these errors depends on how the algorithm is implemented in a given DSP architecture. This error can be reduced by using a larger word length, and for data by using rounding instead of truncation in calculations. Instead of truncation, if you use rounding, that would generally can reduce the errors by using a larger word length. So that is what we just discussed. And coming to the final summarization of the unit, because we have completed the entire unit 1 syllabus with all the videos which are available in the YouTube. In this chapter we just in this complete unit we just studied about various number formats like floating point number format, fixed point number format, double precision format, block floating point format. All these we have discussed, and what applications generally we do use those number formats. And we also studied regarding the dynamic range and precision of those number formats. And coming to the sources of errors, also we have discussed there are different types of errors we generally observe at A to D, D2A, and DSP devices, and that we discussed. And for each category, we have there is an concept of estimation of errors also, that also been discussed. And all these will if we discuss all these things, we got a clear clarity picture of how a DSP computations or how a DSP process of works with respect to all these things is clearly known to us. And in the second unit, we completely discuss about the architecture, how a DSP architectures look like, and what are the different blocks available, generally multiplier, shifter, MAC unit. Okay, these are the major building blocks of basic architectural features of this digital signal processor. And we usually discuss about the bus architecture and memory of it, what are the different types of addressing modes available, what are the special addressing modes available, what is the use of address generation unit in the architecture, and what are the basic features of external interfacing. All those we are going to discuss in unit 2. Thank you one and all for listening to this session. Thank you so much.